Get away from me. You're scaring me. Stop. No. No, don't. Ah! All right. So anyway. What the hell was that? All right. So I got some. I don't know what day it is, okay? But you know I have those science meetings. I don't know if it's Monday or Tuesday. I might not be here. Either Monday or no. It's the whole day because it's a whole.
When's the thing at Judge?
The thing at Judge that I have to do my presentation for is the 8th of March. And
How's that coming along?
oh well, that's what the meeting's all about.
Oh.
Me and my project partner, my buddy, we're gonna get together and via Zoom, and we're gonna put our project together. So yeah, it's gonna be no.
Do you like him?
He's a nice guy.
Okay.
Yeah.
Why is just Judge?
What? Oh, he's not from Judge?
I thought you said he was.
No. The guy I'm working with is from it's at Judge. The guy I work with is Pope John Paul. Royersford, like way up in the.
Oh.
That's the guy I'm working with. Did you? So they got a beautiful campus. They got like nice fields. They're all like AstroTurf.
Their
And,
hockey team's combined with Carroll.
oh, well, yeah, but they got their grounds. It's a beautiful place. Anyway, so I don't know what day it is. Okay. I thought I'd get an email by today. I don't know if it's Monday or Tuesday. So there is a good chance that it's Monday. Okay. If it is Monday, I'm probably going to give you Ed puzzles. Okay. Yeah, they're short. Yeah. I have them already on there for you. I give you worksheets first, then I give you some Ed puzzles to just kind of like wrap things up. So you're getting the worksheets today. We're going to knock you out Newton's second law. We're going to get the 2 worksheets. They're very easy, trust me. And then if I am not here on Monday, say we'll just do the Ed puzzles, okay? But what I want to do now with you is I want to knock you out Newton's second law. You'll have time at the end to start the homework. You'll have the entirety of the weekend and probably Monday to get it all done before we go over any of that stuff.
When's our next lab?
Our next lab is next week. I got to figure it out because the days are shifting, so it's going to be like Tuesday, Wednesday, Thursday. Well, today's at day 6. Tomorrow's day 1. Well, because there's no school tomorrow because it's the flexible instructional day, the day carries over. So tomorrow will be a 1. So now Monday's a 1. See what I'm saying?
Yeah.
So that kind of gets pushed back.
Wait, does that push
So-
back everything now?
Whenever we miss a day of school for any reason, okay, like snow day, whatever the case is, that number day gets pushed back to the next day. So today's a 6.
Right, but is it keep going like all the way through
No,
January?
this is my notes.
What?
All that pushback on the day?
The whole thing, yeah, it's going to be, yeah.
So this is Dormer's test push
Everything gets adjusted, so yeah, Monday will be a day 1.
When? The semester thing.
That's baloney.
I'll tell you what though, I promise, when my presentation's all done, I'll show you guys. And you'll be like, man, that's really terrible. I'm like, I know.
What's it about?
I don't know. I don't know what to look at. No, I'm just kidding. It is about, okay, so
Paying attention?
it's about, so when we do lesson plans, we have these things called standards we have to use. So there are these special standards we use in science. And there's 3 ways there's 3 things we do with them. Was he happy?
Yeah.
All right, thank you.
He was explaining how somebody got a 6 out of 16 on his test.
Oh, that's not bad. So anyway, long story short, my part's going to actually be better than the other 2 parts. So, but it'll bore you to death. All right, so Newton's second law. So we knocked out inertia. We knocked out the first law. And again, that first law, just to review, was that anything that is at rest will stay that way because of inertia. Anything in motion will stay that way because of inertia. If you want to make something stop moving, you have to use force to stop it. If you want to make something move, you have to use force to move it. We also talked about equilibrium. Now, second law is actually kind of a common sense law. The acceleration of an object increases as the amount of total force applied to an object increases. Acceleration increases when you increase the force. think of this. You have a baseball, right? And I'm telling you to throw it as hard as you can. Well, if you want to make it go fast, you're going to throw it as hard as you can. So the more force you use, the faster the ball's going to go. The less force you use, the slower the ball's going to go. That makes sense. That, in essence, is Newton's second law. If you apply force to an object, it will cause it to increase its acceleration. So you throw a ball faster, you kick a soccer ball harder, okay? Whatever you're doing, if you increase the force, you increase the acceleration rate of the object. So the greater the force, the more acceleration. That's kind of common sense. Here's where it gets a little messed up. My equation. Okay, we know the force is measured in newtons. My equation is F equals m times a, or force equals mass times acceleration. Here's where things get a little messy. We understand that if we use more force to do something, or apply more force to an object, it's going to go faster. That makes sense. Things get a little weird when we add mass into the mix, okay? So for instance, let's say you have the baseball. And let's say you have another ball that's the same size, but it's solid steel. If you decided to use the same amount of force on each object, which one's going to go faster? The baseball or the steel ball?
Baseball.
Eh?
The baseball.
The baseball, okay? If the object has more mass, okay, that force we used before, the amount of force we used before, it's not going to be enough. So if the force remains the same, but we change our objects and change and vary the mass drastically, if we're using the same force, we're not going to get the same acceleration. So if we're using the same force on two objects, one's very heavy.
Is Joe McNally to the main office? Bring your stuff, Joe McNally.
One's very heavy and has a lot of mass. One's very light and has a little bit of mass. If we're using the same force, the lighter mass is going to go faster. And again, I say that the idea of Newton's second law is common sense, but when you bring in the idea of mass, things get a little weird. We'll see some pictures coming up too that kind of explains this idea between force and mass and acceleration. Again, if it's the same object, you have the baseball, okay, you throw it like, with, say, 25 newtons of force, it's going to accelerate. You throw it with like 50 newtons of force, it's going to go even faster. Whereas if you're throwing the ball, the steel ball and the baseball with 25 newtons of force, the baseball is going to go faster than the steel ball because it has more mass. Again, it's a very simple formula. F equals m times a. We're just multiplying. So it's very easy to manipulate the formula and do the problems, which is what we have for homework. Everybody good here with this? Everybody good? Okay. All right, so look at these two pictures here. All right. So the first picture, I like to just say that the first picture that you see there, small mass, let's say it's a marshmallow. I don't know, I just always said it was a marshmallow. And we see a car, what looks like a car. Now, look at the vectors for force, okay? So the vector behind the marshmallow is the same size as the vector behind the car. It says same force, small mass, large acceleration, larger mass, small acceleration. And again, that's what we're talking about. If we're going to use the same amount of force to move two objects, the lighter mass, the smaller object, is going to accelerate at a greater rate. Now, if that picture didn't do it for you, the second one, which is kind of comical, really brings it home. So we have a golfer, okay? And he's got a putter, and he's going to use force to putt a golf ball, right? So you can see in the picture next to the man, there's a little red F, then it says equals, then there's a tiny little M and a big A, okay? And the idea there is, with the force he's using on that little mass, it's going to accelerate greatly. Then they show the same guy standing behind a truck. He's going to hit the truck with the golf club to make it I mean, obviously it's not going to work, but just for, purposes of understanding, he's going to hit the truck to make it move with the golf club. Notice the two F's are the same size. Notice now that the mass is really big. And it might be even hard for you to see it, but the A is really small. That A there, in my opinion, should be like microscopic. Is he ever going to make that truck move with a golf club? No. Okay, he might dent the bumper of the truck or something. He's not going to make the truck move. But the idea is pretty simple. Using the same amount of force on two different objects of varying mass. The smaller mass goes faster than the larger mass with the same amount of force. If he wanted the golf ball and the truck to move at the same speed, same acceleration, he'd have to use a lot more force on the truck. Any questions about this? It's pretty, again, it's kind of common sense. All right. So on the board it says, may the mass times acceleration be with you. That is meant to be funny. Anna, why is that funny? What's it really say? And also with you. Yes, it says, may the force be with you. Mass acceleration, force, farmer joke. I thought it was funny. All right. I actually have a poster that I just never put up.
Where's
I think
that
it's-
then?
I think it's cute. Huh?
Where's that?
It's probably in my closet. I just never put it up. All right, force problems. Here we go. So here's our first force problem. How much force is needed to accelerate a 1,400 kilogram car at 2 meters per second squared? Now again, these problems, I used some easy numbers here for this. These problems are very easy. Our formula is F equals M times A. We're going to plug our numbers in. We get force equals 1,400 kilograms times 2 meters per second squared. And again, I use some easy numbers here. John, what's my answer?
2,800 newtons.
Excellent. 2,800 newtons, you would give me the unit. Beautiful. 2,800 newtons. So if I'm asking you for force, and I'm giving you the mass and the acceleration, multiply them together, you got your force. Okay, second problem on the same slide. How much force is needed to accelerate a 70 kilogram rider and his 200 kilogram motorcycle at 4 meters per second squared? Now, sometimes you get a question like this, and it's important to remember that, well, the motorcycle is not going to drive by itself. So we have to add the rider's mass of 70 to the motorcycle's mass of 200. We get 270 as our total mass. We use our formula, F equals M times A. We plug our numbers in. We get 270, which is our total mass of the rider-bike combination. 270 times 4. And our answer here is, Pat, what'd you get?
1080.
1080. Very nice. 1,080 newtons. Again, these problems, this is easy. This stuff's easy. Now, this is the, I hate to call the calculating that force stuff math, but it was kind of like a little bit. Look at some of that on your test, okay? You have this formula. I'm going to show you the two variations if you're looking for acceleration or mass. Then we have two more formulas learned at the very end of the chapter when we talk about friction. And they're easy too. Everybody good here with this? Everybody good? Yeah? All right. So look at the two variants. A force of 100 newtons is applied to an object that accelerates at a rate of 2 meters per second squared. What is the mass of the object? Okay, so our first variant of the formula. We know that if we are looking for force, it's mass times acceleration. If they're giving us our force and they're giving us our acceleration, we divide force by acceleration to find our mass. So our formula is m equals F divided by A, force over acceleration. You plug your numbers in, you get 100 newtons divided by 2 meters per second squared. Now, the other thing with these problems when you're writing them out, worksheets and things, what you got to remember is with these problems, every member has its own unit, okay? So if we're looking for force, it's newtons. In this case, we're looking for mass, so it's got to be kilograms. If we're looking for acceleration, you got to remember it's meters per second squared. What's my answer? Is a tough one. What's my answer? John, what's my answer?
50 kilograms.
50 kilograms.
Mr. Sam,
Yes.
could you also just plug it into the original equation and do it like how you do it in algebra, or you have to
Yeah.
change it into that?
Yeah, you can do it. Yeah. You should see the stuff we do with this stuff in AP. It would scare the crap out of you. We've been working on the same stuff that we've covered here. I've been working with them on this stuff since the end of November, and we still haven't finished uni yet because it's so much. Like you have no idea. You have no idea how easy this is compared to the AP stuff. You have like no idea.
I have an idea.
Oh, it's frightening. Teaching you guys this is fun. AP's like, oh man, I gotta do some work today. With you guys, it's like, oh, this is easy. All right, last one. I'm sorry if this one got messed up with the stupid screen. If a 40 kilogram person on a 10 kilogram sled is pushed with a force of 300 newtons, what will be the person's acceleration? Okay, now again, we got a person who's 40 kilograms and the sled that's 10, so we got to add those together, that's 50. The formula we're going to use here for this is A equals F over M. You plug your numbers in, you get 300 newtons over 50 kilograms. Another easy problem here. I picked some easy numbers. What's my answer going to be? Meters per second? Pat, what'd you get?
6 meters per second squared.
You got it. Our answer is 6 meters per second squared. Now, there are some applications to this, which I'm just going to talk about for a second. We're going to see them. We're going to do Newton's third law, and then we're going to talk about the applications more, because I made it its own thing called weight. One of the applications that we use with this formula, and you'll see this next week, is calculating weight. Now, you see these numbers up here in kilograms, okay? To find the weight of an object in newtons, you simply multiply it by 9.8. The formula for this, what we're going to learn, is F subscript G, force of gravity, equals mass times A subscript of G, which is 9.8. Gravity pulls everything down on Earth with the same rate, right? Free fall, 9.8. So to calculate an object's weight in newtons, which we're going to have to do, you take that weight, you take the mass, times that by 9.8, throw newtons at the end of it, and you got your answer. That's one of the applications that we're going to see used from Newton's second law. So using Newton's second law, we can actually figure out the weight of an object in newtons. Force also happens when things move around in a circle. We're going to see the application of that used a couple chapters from now. We'll learn about circular motion. There's something called centripetal force. It's force equals mass times acceleration, but there's an extra little thing added to it. So we're going to be using this quite a bit. So the application of finding the weight of an object in newtons, we're going to be using that. We'll be using the circular motion force. So force is a pretty big deal in physics. We're still not done anywhere near done the chapter yet. We're getting close. We have to finish off Newton's third law, weight, and then we're going to end it with friction, which is going to give us our last equation. I think. I forgot about that. We got. What do you think at the end of this? Okay, so we're not done yet. We got two football players. Okay. We have Alex and Jason. They collide head on. They have the same mass and same speed before the collision. How does the force on Alex compare to the force on Jason? What do you think? We got two football players of the same size. They hit each other head on. I don't mean like head on, like head to head, like they go to tackle each other basically. What's going to happen to these two guys?
Just go bounce right off each other.
They're going to bounce off each other. Why? Because they have what?
Equal force.
Equal force. Okay? If you got two guys who hit each other with the same force, same mass, same speed, same force, okay? They're going to bounce off each other. You see this happen a lot. Think of two billiard balls. You push them towards each other, they hit and they bounce off, right? They bounce off each other and roll backward away from each other because they like transfer the energy. Same thing here with this example. Now let's change it up. Suppose Alex now has twice the mass of Jason. John, what happens now?
Jason will be pushed farther back.
Mm-hmm. Jason's going to get pushed farther back. Is Alex going in Jason's direction too?
Yeah.
Or should I say, is Jason going in Alex's direction? Yeah. Alex isn't bouncing off of nothing at this point. He's plowing through. So if he's running to the right and Jason's running to the left and they collide, Alex has twice the mass. Alex is going to keep moving in his direction, so is Jason. Now, worst case scenario, suppose Alex has twice the mass and Jason's at rest. He doesn't even see him coming. How bad is that going to be? Rob, how bad is that going to be? That's bad. That's real bad. Okay? So when Alex hits Jason at rest, it is just going to be brutal. It's going to be nasty. Okay? But again, that's Newton's second law. Any questions? Because that's pretty much it. That was fun. That was fun. All right, so let me show you the homework. When we do collisions, which is coming up when we do momentum, I like to talk about football, and I show you some videos of like people getting sacked and hit, and it's all fun. And there's car crashes too that are also fun to watch. All right, let's get out of here. All right, so let me get out of there. All right, so let me show you the homework. Again, we got 10 minutes. You can get some of it done now. Again, as far as, I'm going to change the date on this, when it's due. When I find out, I should find out tomorrow when my meeting is, okay? I'm gonna change this to Monday's date for you guys. Okay, and then this one, change this one too. Change it to Monday. Okay, all right, so let's look at the first worksheet. All right, so we got force problems, guys. Worksheet, force problems. All right, so for the force problems, these are just simple word problems, okay? So you got 1 through 14 problems. Again, it's a mixed mash. I might ask you to find the mass of, or the force of two things. I might ask you to find the force, acceleration, the mass, whatever mass can, just some typical random force word problems. The second worksheet, I really like the, it's a little bit different. The first part is my favorite part. So in the second worksheet, we start with what's called to the finish line. And what we're going to see here once it loads, come on. All right, it says the force applied by contestants A, B, and C is equal. The masses of the objects are being pushed or indicated. You got 5 kilograms, 2.5 kilograms, and 0.5 kilograms. Based on information, answer the following questions. So using the picture, you're going to answer questions about acceleration, and then 5 and 6, you're going to do 2 little problems with the data they gave you, okay? Now, obviously, in the picture, A, B, and C, if we're using, say, 50 newtons of force, each contestant, A, B, and C, is using 50 newtons of force, which one should go the furthest? Based on that.
Tiny one.
The little one, C, okay, the 0.5. Remember, if we're using the same amount of force, what we should see happen there is the smallest mass should go the furthest. What if the accelerations of all of these objects were the same? What happened to your force?
The force is more on the 5 kilogram than it is the 0.5.
Good, okay? So, and that's all you're going to do, guys, basically. Again, you're going to just, look at things here and just trying to figure that out. It's pretty easy. But I like the visual of this because it really helps get that idea where you throw mass into the mix. Then there's a couple of word problems here and a couple more word problems and some just written questions here. That's pretty much it. Okay, so like I said, these 2 worksheets, you got force problems and then Newton's second law of motion worksheet. These 2 are I'm gonna have one there due Monday. If I find out that Monday is the meeting, which I hopefully I'll find out tomorrow. If the meeting's Monday, I'll change that to Tuesday, and we'll go over it Tuesday. But either way, you have until at least Monday to get this stuff done. So you got the 2 worksheets. You have your article that's due tomorrow. That'll be your snow work. I'm actually going to take the article out of the folder, okay? Put it on the main page, and then at the end of it, put in quotes like snow day, so that they don't know anything. I probably shouldn't have said that because I'm being recorded, but sorry. So anyway, the point is, okay, you got enough work to do between the 2 worksheets and everything else. Again, anybody who missed any of the ed puzzles, you got those to make up too. So please, make sure you get that done.
I don't know who's in that one.
Any questions, guys? Because that's pretty much it. Okay. What happened?
No assignment, just a message.
Mr. Skip Beauty just sent us a reminder saying, enjoy this McDonald's.
Oh, that's nice.
We have no work.
Yeah,
That's so nice.
We have an ed
Miss
puzzle.
Knox is gonna give us like a 5 paragraph essay to do.
No, bro, we got it. That test review.
For Nosco? We're gonna do it?
Guys, don't forget, everything's going to get pushed back date-wise, so our numbers are going to change. So Monday's going to be a 1, Tuesday's going to be a 2. Friday would be a 5. I'm thinking we'll probably have our test on Friday. Because we're almost done. We're almost on the chapter. By Friday, we should be done.
Wait, acceleration is force. Wait, no.
Mm-hmm.
Force divided by mass?
Mhm. Yeah.
The whole essay for an absence assignment. I'm saying she did, but we have one. It's Tuesday.
Newton.
Like, that's insane. When we do it.
What's the acceleration thing?
The unit?
Per second?
Meter second squared.
You stop the recording.
Oh, yeah.